So in this module, I'd like to focus on one of the assumptions that we made in our analysis of the BB84 protocol and explain how this assumption can be removed. So this was the assumption that the rounds that are tested by Alice and Bob are the same rounds that are used to make the raw key. Of course, that's an unrealistic assumption. And the goal in doing this was that because the rounds are tested, we knew that Alice and Bob's outputs were the same in those rounds, and this let us bound the probability that Eve was able to guess the same outputs via the analysis of the guessing game. Now, what if the rounds that are tested are not the rounds that are used for the raw key? Intuitively, the same result should hold because we're choosing the rounds for testing at random, and if Eve cannot guess these rounds, then she shouldn't be able to guess the rounds that are used for the raw key either. But in order to prove this formally, it relies on very powerful inequality that are called concentration inequalities, and I want to give you one version of such an inequality that is the version that is needed for the BB84 protocol, and that's quite a strong version of the inequality. It can be extremely useful. So let me tell you what the inequality says. The setup is the following. Suppose that you have a random variable z which is made of, let's say, 2n bits. And this random variable is completely arbitrary. I'm not assuming that the bits have a certain distribution, I'm not assuming that they're independent, I'm not assuming that they're unbiased, nothing at all. Now there's a second random variable, call it t, and this one I'll assume that t is simply chosen as a uniformly random subset of the integers 1 from 2n of size n. And now here's what the inequality says. It says that the probability over z and t that two things happen. First of all, if I look at all the indices that are in t and sum the values of zi, I would observe something, a total sum that is less than delta n for some delta. And at the same time, when I sum over the indices that are not in t, I would observe something that is bigger than delta plus a little bit more, some nu times n. The inequality says that this probability is always going to be at most exponentially small in nu squared times n. So this is why the inequality is very strong. It's not making any assumptions on the distribution of z. Whatever the z are, they can be very correlated. It's saying that if you choose a random subset t of locations, and if you observe that the sum of the zi's for the indices in t is small, then the chance that the sum of the zi's for the indices not in t is substantially larger by some amount nu than the sum that you observed in the indices in t, then that probability is exponentially small in nu squared times n. So you can already see, I think, how this inequality will be applied in the analysis of the BB84 protocol. The idea is to set up a special variable zi. Zi will be equal to 0 if Alice and Bob's ith outcomes for those rounds that were not discarded, so when their basis choice is the same, agree, and 1 if Alice and Bob's ith outcomes disagree. So then in that case, the test that is performed in the protocol is exactly choosing a uniformly random subset t, like the one that is here, and checking that the sum for I in t of the zi's is at most the error tolerance, delta, times n. And the inequality here will say that as long as this is the case, then the chance that the number of errors in the rounds t bar, so the complement of t, those rounds r that are used for the raw key, is much larger than the observed error, is exponentially small. And using this, we'll be able to wrap up the analysis as we did in the previous video. So this inequality is very strong. You'll see more of it in the lecture notes, and it's well worth thinking about and remembering.